There's a gray cylinder sitting on a pole outside your house, or a house-sized gray box humming behind a chain-link fence somewhere in your city. Almost nobody has ever thought about what's inside it. You'd notice if it disappeared. Every home downstream of it would go dark. And every few months, somewhere in the country, one of these things fails badly enough to make the local news. Usually described the same way. A transformer exploded. A fireball. Smoke visible for miles. That's a strange way for a piece of electrical equipment to fail. Here's what's actually inside one, and why the failure looks like that. Strip away the tank and the fluid and the hardware, and a transformer is genuinely simple. 2 coils of wire, wound around a shared iron core, never touching each other electrically. Alternating current flows through the first coil, the primary, and creates a magnetic field that constantly changes direction 60 times a second. That changing field travels through the shared core and induces a voltage in the second coil, the secondary. No wires cross. The only connection between the two sides is the magnetic field itself. The ratio of turns of wire on each side sets the ratio of the voltage. More turns on the output side, higher voltage out. Fewer turns, lower voltage. That's the whole trick that lets the grid step voltage up for efficient transmission and back down to something safe for your house. One detail that matters later. The core isn't a solid block of iron. It's built from hundreds of thin iron sheets, each one coated in insulation, stacked together. If you used a solid core, the changing magnetic field would induce its own swirling currents inside the metal, eddy currents, which do nothing but generate waste heat. Laminating the core chops those currents down to almost nothing. That core and coil assembly still has to go somewhere. In any transformer big enough to matter to the grid, it goes inside a sealed steel tank, completely submerged in oil. The oil isn't there for one reason. It's doing 2 jobs simultaneously. First, insulation. Inside that tank, you have windings sitting at wildly different voltages, packed close together. Air alone can't reliably keep those voltages from arcing across the gaps. Oil can. A good transformer oil has dielectric strength many times higher than air. Second, cooling. No transformer is perfectly efficient. Some energy is lost as heat, both from resistance in the windings and from those small residual losses in the core. The oil circulates, sometimes just through natural convection, sometimes pumped, carrying that heat out to radiators on the tank's exterior, where it dissipates into the air. So the same fluid that's keeping 10,000 volts from arcing across a 2-inch gap is also the thing keeping the whole assembly from cooking itself. That dual role is exactly what turns an electrical fault into something much worse than an electrical fault. Here's the mechanism, and it's more specific than the oil catches fire. Say something goes wrong inside the tank. Insulation that's degraded with age, moisture that's worked its way in, a surge from a lightning strike, a severe overload that pushes the windings past what the cooling system can handle. Any of these can trigger an internal arc, a burst of electrical current jumping somewhere it shouldn't. That arc doesn't just heat the oil around it. It's hot enough, sometimes thousands of degrees, to instantly break the oil's molecules apart. Transformer oil is a hydrocarbon, and when you tear a hydrocarbon apart with that much energy, it doesn't turn into more oil. It turns into gas. Hydrogen, acetylene, methane, ethylene, all flammable, all forming essentially instantly at the arc site. A sealed steel tank does not have anywhere for that gas to go. Pressure spikes, fast enough that in a severe fault, the tank itself can rupture before any protection system has time to fully isolate it. When that happens, you get exactly what shows up on the news. A burst of flammable gas and atomized oil, meeting open air, meeting an active arc. That's the fireball, and that's why these failures look explosive instead of just smoky. Because this failure mode is so well understood, the industry built a diagnostic specifically around it. It's called dissolved gas analysis, DGA for short. Utilities periodically pull a small oil sample from a transformer and measure exactly which gases are dissolved in it, in what ratio. This works because different problems produce different gas signatures. A transformer that's simply running a little hot produces one gas profile. One with a low-energy internal spark, what's called partial discharge, produces another. A full-blown arc produces a third, distinct profile dominated by acetylene. It's effectively a blood test. You're not waiting for the patient to collapse. You're reading the chemistry for a specific problem you already know how to recognize, because you understand exactly how that problem forms. Utilities take that seriously enough to sample transformer oil on a routine schedule for exactly this reason. Here's the part that turns this from an interesting failure mode into a genuine grid resilience concern. The transformer on the pole outside your house is a commodity part. There are spares. That's not the one that worries planners. The large power transformers, the ones at substations, stepping transmission level voltage down toward distribution, or stepping generation up onto the grid, are not commodity parts. Most of them are essentially custom-built for their specific application. A meaningful share of the ones installed in the US are manufactured overseas. And building one, start to finish, isn't a weeks-long job. Industry lead times are widely documented, running well over a year, sometimes closer to 2. Which means that if one of these fails catastrophically, the exact failure mode from a few minutes ago, there often isn't a matching spare sitting on a shelf somewhere. You can't 3D print a 200-ton piece of custom electrical equipment. You order one, and you wait. This is a known problem. Utilities and the Department of Energy have spent real effort on it. Spare equipment sharing programs, some strategic stockpiling of critical spare units. None of it adds up to what you'd call a deep reserve. The US does not have a large strategic stockpile of large power transformers sitting ready to go, the way it does for some other critical materials. A machine most people can't name, that most people have never once thought about, is one of the grid's real single points of failure. That gap hasn't been closed yet.